All right, in our last set of video notes for this molarity solutions unit, we're going to talk about a concept called dilutions, which sounds exactly like what you would connect it to. If you've ever gotten like a pop at a restaurant and you forgot to sip it for a while, and a half an hour later, it tastes really watered down. It doesn't have as strong a flavor because the ice melted and it kind of, well, really watered it down. That's what we're looking at here. Okay. So if we have a really concentrated solution and we want to use more of that liquid volume, we can dilute it by adding water, increasing the volume, but it keeps the moles of solute constant. Okay, because not all chemical reactions require the most concentrated saturated solution to have the reaction run. So to prolong the use of our chemical, what we can do is add water to it and dilute it so that we get a larger volume of solution to work with, and we can get more experiments and more trials out of that total solution. So this image off to the right shows two very important things. One is we see that as the volume increased, the color kind of lessened. So that means that these blue particles are less concentrated after the water has been added, right? So we cause the system to kind of weaken a little bit, lower in concentration by adding water, adding more solvents, and therefore we get more volume to work with. And then these zoomed in images here, the blue particles are our blue solute, and the pink particles are the solvent, which we're going to assume is water. We notice that they're still present, but there's just a lesser ratio of them. So the important thing here is that the moles of solute stay constant. All right, if I make a pitcher of Kool-Aid and then pour that into one of those giant 5-gallon Gatorade coolers that they have on like the sidelines at sporting events and just fill that up with water, it's not going to be the same taste and the same, flavor of Kool-Aid. It's going to be really watered down because it was the same amount of Kool-Aid packet, but just at a smaller ratio, right? So when we go through these dilutions, the fact that we're keeping moles constant means that we have one really simple equation. This is our dilution equation that we can use to determine some changes in the molarity and some changes in the volume. So it looks complicated only because we've got these numbers connected to it, but the 1 and the 2 just stand for like initial conditions at the very beginning and final conditions at the end after we've made a change to it. So anytime you've got variables next to each other, it's assumed that they're multiplied. So the equation can be interpreted as saying the initial molarity, M1, multiplied by the initial volume, V1, is equal to the final molarity multiplied by the final volume. Because molarity times your volume gives you the moles of solute, and because it's constant, we know that that allows us to bridge the before and the after conditions using that equation. All right, so if I start with 100 milliliters of a 4 molar solution, so we've got V1 and M1, and then add enough water to make a final volume, V2, what is the final molarity? M2. So if we rewrite our equation, M1V1 equals M2V2, we can plug in the three components that we have and figure out what is this smaller watered down molarity as we went from 100 milliliters to 1 liter, right? Now it looks like our volume went from 100 down to 1, but what we have to watch for is the fact that we started with milliliters and we ended with liters. So really we went from 100 milliliters to 1,000 milliliters, and we added 900 milliliters of water to make that happen, right? Now the trick for this equation is just to make sure that V1 and V2 have the same units, because ultimately they're going to be divided out. So we want the units to be the same so that when we divide, they're going to cancel out. So we could convert this to liters, or we could convert this to milliliters. We'll still get the same answer because we're going to be dividing them out in the end. So I'm going to say that 1 liter is the same as 1,000 milliliters, and we can plug that right into the equation. So initial molarity was 4 times the initial volume, 100 milliliters. We're solving for M2, and our final volume is 1,000 milliliters, not 1 liter. So we got to simplify these two numbers. We got 400 is equal to 1,000 times M2, and then we're going to divide both sides by 1,000, and M2 is now equal to 0.4 M, right? So we took our volume and went from 100 to 1,000. It went up by 10. So what happened to our concentration? It went down by 1/10, okay? So that pattern is not, atypical. That's pretty common. If we double our volume, we have our concentration. If we triple our volume, our concentration goes down by 1/3. So it stays in that same mathematical proportion. Right? So I want you to try the next two problems. Really pay attention to the way that the information is worded, and then we'll resume the video and talk about the solution. All right, so here it says, how many milliliters of a 2 molar solution would you need to prepare 100 milliliters of a 0.4 molar solution? Since a dilution is always a weakening of the concentration by adding water, this smaller molarity is our M2, and we want to end with a final volume of 100 milliliters. So when it says how many milliliters of a 2 molar solution, we're solving for V1, given that our initial molarity, M1, was 2. Oops, that should be a little one. Okay, so M1 V1, 2 molar times our unknown is equal to M2 times V2, and we ended with 0.4 molar and a final volume of 100 milliliters. So now this is equal to 40, and then 2 times V1, we're going to divide both sides by 2. So V1 is equal to 20 milliliters. Okay. Again, if you go from 2 down to 0.4, that's going down by 1/5. And so our volume had to go up by a multiple of 5. Right? So how much water needs to be added to the previous question? If we start V1 with 20 milliliters of this higher concentration, and we want to end with a final volume of 100 milliliters, so we want to end with 100, we start with 20, so how much do we need to add? The difference between the two is 80 milliliters of water, so that we end with a total final volume of 100. 80 milliliters plus the 20 milliliters of this 2 molar solution will give us that volume with that final concentration.